Uh, okay, so good afternoon. So we'll welcome back to the live discussion sessions on mechanics and control of robotic manipulators. So I hope I'm audible. Uh, could you confirm, Saurav, whether I'm audible or not?
Yes, sir, you're audible.
Okay, thank you. So yeah, this week we'll be mostly discussing with the topics regarding dynamics of robotic manipulators. So I suppose like on the week 5 itself, the lectures have been started. We have actually came across lectures regarding dynamics, but the assignments were only concerning the questions regarding up to velocity analysis. So last week we haven't discussed anything about dynamics, but this week, since the questions are more the questions in the quizzes are more uh, aligned to dynamics, we'll discuss some key concepts in dynamics, right? But due to the fact that we'll also have trajectory planning in this week, we are not covering trajectory planning during this discussions for this session because the, the quizzes does not have questions regarding its trajectory. That will come on week 6's quizzes. So yeah, with that, I suppose we can start the session officially regarding dynamics. Although the title says week 5, it covers trajectory also. We'll limit our discussions with dynamics because, as I've already said, the quizzes are only concerned with the dynamics of robotic manipulators. So moving on, we'll basically discuss the key concepts regarding dynamics, because as you might have come across the formulations, it's quite lengthy, especially the Newton-Euler method. It's a bit detailed because there are lots of equations that you will have to study. And we are not basically deriving these equations, the Newton-Euler equations, because it's out of scope of this work. But again, the principles, you can find the principles of the rigid body motions in any textbooks regarding rigid body dynamics, any textbooks from rigid body dynamics. Okay, so moving on, we'll mostly start with dynamics. So it basically concerns with how the state of a robot changes from one time to another. That is basically what the dynamics is all about. But from robotics perspective, it says in mechanical systems such as robots, the change of state basically involves motion. So the change of state from one state to the another, it basically involves motion, and it also involves the forces, because it's the forces that could be causing the motion, and as a result of motion, you would be encountering some sort of forces in all of these joints, right? So the second point basically says, in other words, the dynamics, it's a science of motion, right? It describes why and how a motion occurs when forces and moments are applied on massive bodies. So this is strictly concerning with robotic systems, or in case like mechanical dynamics, that concerns with dynamics of mechanical systems. So it's basically a mapping. It's basically a study of motion involving forces. Earlier, we have seen the pure kinematics case where we are not considering the cause of motion. We are only studying the motion, that is kinematics. We didn't basically consider the cause of motion. But here we are also concerning the forces, the cause of motion, that which are forces as well. Yes, and here the third point says the motion can be considered as evolution of position, orientation, and their time derivatives. So here the motion of a mechanism or a robotic mechanism does not limit itself with the position alone. So if I'm denoting Q as the position coordinate, we are not limiting our study with position alone. We also consider their velocities as well as their accelerations, right? So basically, in the domain of robotics, strictly within the domain of robotics, it says the dynamic equations of motion of manipulators is utilized to set up fundamental equations of control. So deriving something called equations of motion or the governing equations are fundamental in deciding, establishing robot motion control. Like if you want to control a robot to specify to track a given trajectory, it is important that we should be able to model the robot's equations of motion. So the equations of motion is basically the mathematical model that governs the behavior of the robot, how the robot behaves for a set of, if we are inputting a set of forces or if we are giving a set of trajectory commands, how the robot would move based on the inputs that we give, right? So coming on to the next step, we'll talk more about equations of motion, which are nothing but the governing equations of how a robot moves. It says the way in which the motion of robotic system arises from torques force applied by the actuators or from external forces moments applied to them, right? So in general, we have, for example, if we could consider a 2-hour robot, right? We could apply, the robot is essentially subjected to external forces and moments, right? So if we task or if we make this robot to execute some tasks that involve some gripping or some pick and place, since its end effector would be subjected to some forces and torques, maybe some forces F vector, it's not Fx, a force vector as well as a moment vector as a part of its task. It could also be subjected to external forces and external moments, could be acting throughout the entire for all the links of the mechanism. So how the robot reacts to the forces as part of its task and as part of these external forces, how the robot reacts to this the forces, the set of all the forces, is basically governed by the equations of motion of the robot, right? So this is nothing but a mapping of the joint torque. So here in this regard, the torque, the Greek symbol tau means the torque acting on all of these active joints. Torque or forces. This does not mean the unit should be in torque. This is a generalized vector comprising of forces as well as torques. So depending upon the kind of joint, if it is a prismatic joint, tau means force, or if it is a revolute joint that we are concerning about, the Greek symbol tau means the torque, basically. So it says this is basically a mapping or a function between the mapping between torques acting on all the active joints and the trajectory of each of these joints. Q dot, Q double dot are basically the trajectory of all the active joints within the robot. And more with, if you are writing this with more clarity, this is nothing but this equations of motion. Tau is a mass matrix. We have a mass matrix times the acceleration vector plus another vector that is, we basically call this vector as a vector of Coriolis and centrifugal effects, right? So this is how an equation of motion would look like. Like we all know what an equation of motion of a single rigid body would look like, right? Like if we have a spring mass system, equations of motion regarding the spring mass system is nothing but the external force, sum of all the forces acting on this rigid body is mass time acceleration plus the forces that is acting due to the spring force, mx double dot plus kx. So similar analogy is happening in robotic systems, but this is the context is not with respect to a single body, but this equation of motion is regarding multi-body. Actually, this is nothing but a multi-body dynamics formulation because it consists of all the forces and torques and all the motion parameters regarding all the rigid body members of a robotic system. This is what we basically call a multi-body dynamics equations of a robotic system, or you could also call it as an equation of motion of an entire robotic system, right? And what it says is that derivation of equations of motion for the system is the main step in dynamic analysis of the system, since equations of motion are essential in design, analysis, and control of the system. So the governing equations of motion of a robot is essential for critically the three critical instances, such as design, analysis, and control of the system. Right? We'll try to give more clarity regarding each of these terms. So yeah, moving on, it basically says robodynamics is a study of systems that undergoes change of state as time evolves. So if a robot is at a state, maybe governed by its position coordinates, q of t, q dot t, and q double dot t, what would be the position of the robot at a different instance? Q of t plus 1, sorry, q of t plus 1, q dot of t plus 1, q double dot of t plus 1, right? So how a robotic system evolves as time goes on, right? So this entire evolution of the state of a robot is governed by the equations of motion, right? So yeah, and the change of state is basically a broad term. It does not necessarily mean it should be motion parameters or trajectory coordinates. Like, but in case of robots, the change of motion is exactly characterized by the change of position, velocity, and acceleration coordinates. That's what this point says. In mechanical system, such as robots, the change of state involves motion, right? And in other words, dynamics is the science of motion. It describes why and how motion occurs when the forces and moments applied are applied on massive bodies. So as the consequences of the forces and motions, the equations of motion evolves. That is what governs a robot to move from a state t to the state t plus 1. Right? And the third point says the motion can be considered as evolution of position, orientation, and their time derivatives. Right? So the entire position, its orientation, and their derivatives are all considered to be states of a robotic system, which in terms characterize just the motions of a robotic system. And the states, the position orientation can be basically characterized by the joint coordinates qt, q dot of t, and q double dot of t. Depending upon how the trajectory parameters varies, the position, the orientation, the position, velocities, and accelerations, you could basically manipulate how the position and orientation of the robot varies, as well as their time derivatives. So point 5, it says in robotics, the dynamic equation of motion for manipulators is utilized to set up fundamental equations of control. So we'll basically deal with all these things in upcoming weeks, how we would be using the equations of motion in designing a controller for robotic mechanisms. Because deriving the robot dynamics, which is given by the equations of motion, is essential for developing a controller of a robot. So how to do so, we will come across in upcoming weeks. So just like what we have discussed in kinematics, we also have two key terms called forward dynamics as well as inverse dynamics. So if you can recall, we had forward kinematics, right? Like if the kinematics of the robot, we had a task space coordinates, and we also have joint space coordinates, right? And the mapping from task space if task space is given, finding the joint space coordinates is nothing but inverse kinematics, whereas the other way was forward kinematics. And a similar analogy also exists between dynamics also, where we have already established that dynamics is nothing but the mapping between the torques and the trajectory of the robot, characterized by q dot, and q double dot. Right? It's basically a mapping between the forces of the robotic system and the trajectory. So what it says for forward dynamics, in fact, is that for a given input vector tau and the known states q and q dot, find the resultant motion of the manipulator, or in other words, find q dot. So we all know that the equation of motion of a robot is something like mx double dot plus some vector, a function of q and q dot, is tau. So if we are given this torque, if we are basically supplying the torque to each of these actuators. So like I'll take a simple example. If we have a 2R manipulator, right? So this is the first joint R1, this is the second joint R2, right? So if I'm applying some torques on each of these joints, maybe if I'm applying a torque of tau1 onto this joint and a torque of tau2 to this joint. So our vector tau will be comprising of the two torques, tau1 and tau2. So if we are supplying an input vector tau, what would be the, how would the robot respond, or how would the robot move, right? So what it essentially says is that if tau is given as inputs, if this is input, then what are the trajectories? What is the trajectory of the robot? So in essence, what it does is that it basically writes the unknown in terms of known. So here we basically know the m. This is nothing but the mass matrix. So depending on the robot and the weight of each of the individual bodies, we'll be able to assemble a mass matrix. We'll also be able to assemble this n vector that is comprising of forces contributed by centrifugal and Coriolis effects. And the unknown would be this x double dot. We don't know how the robot would move. Okay, so like to maintain the homogeneity of units, q double dot is the unknown. How would we find out this q double dot for a given tau? So by doing some simple elementary mathematical manipulation, we could write this equation as tau minus n of q dot whole multiplied by m inverse. This will give you q double dot, the acceleration coordinates. And you can use some integration methods, integration schemes to find out. From the q dot, you will be able to find out q double dot, you will be able to find out q dot and q of t, right? By successive integration. Integrate, and again further, you integrate. Velocity, from velocity, if you integrate, you will get position coordinates. So this is nothing but the forward problem. So if you are giving a set of torques onto each of these joints, how would the robot behave, or how would the robot respond to the forces that we are giving onto the torques? So again, analogous to the forward kinematics problem, this is also somewhat similar to simulating or analyzing the manipulator, right? Just to see how the robot would move for a given input to each of these joints, just to identify or just to understand how the robot moves. That is nothing but simulating the robot, but considering the forces and the movements, simulating the robot and simulating or analyzing the manipulator. Just like the forward kinematics that we have seen earlier. Whereas in the case of inverse dynamics, in case of inverse dynamics, the concept is more or less similar to inverse kinematics, where if you are given a task to control a robot through a trajectory that is characterized by q dot and q double dot. For example, again, we have an instance of a 2R robot. This is the first revolute joint. This is the second revolute joint, R2. So we want each of these joints to move along a specific trajectory. So if you want the first joint to move with as per the trajectory q of t, sorry, q1 of t, q1 dot of t, q2, sorry, q1 double dot of t, and we would want the second joint to move as per q2 of t, as per this trajectory, q2 dot of t, q2 double dot of t, right? If this is how we want to control the robot, then what should be the forces that we would be giving onto each of these joints? So that is the inverse problem, right? Again, from the equations of motion, if I'm writing this equation of motion as such, m of q, q double dot plus n of q, q dot would be tau. So if we are specifying the trajectory of the robot in terms of q, q dot, q double dot, then what would be the tau? Tau is the unknown. How much torque we should be imparting onto each of these joints so that the robot can achieve the desired trajectory. So that is the problem of inverse kinematics. And opposite to what we have seen in forward dynamics, this is a scheme of controlling the robot. This is similar to, this is similar to controlling the robot. So it's exactly analogous to what we have seen in case of kinematics. In dynamics as well, the same concept or the same ideas applies. Where in the forward kinematics, our objective is to find how the robot moves, just like simulating a robot. Like if we are giving a set of input forces onto the robot arm, how the robot would move. And in case of inverse dynamics, if you want to control a robot so that it can trace a particular trajectory, what should be the input forces that we should be giving onto all the joints? So that is more or less similar to controlling the robot. So that is what inverse dynamics is all about. And as you might have observed, you can see how important deriving these equations of motion is, basically because it will give you more important insights to simulating the robotic manipulators as well as controlling the robotic manipulator. But we haven't so far discussed how to derive whatever we are seeing here, these equations of motion. We haven't so far touched that topic. So in order for us to derive these equations of motion, I'll write this over here, equations of motion, as mass of this m matrix times q double dot plus the vector of Coriolis and inertial effects will give you the torque. In order for you to derive this equations of motion, there are two schemes, as you might have come across the lectures. We have something called an Euler-Lagrange method. This is an energy-based method. And if you have tried problems using either of the methods, the Euler-Lagrange and the Newton-Euler method, you might have observed that using Euler-Lagrange is much easier than using Newton-Euler for smaller robotic systems, or in the sense robotic system that has fewer number of links, right? So what does Euler-Lagrange formulation says? It says, since we are considering the system as a rigid body system, the Lagrangian can be defined as the difference between kinetic energy and potential energy, right? So the first step is to derive a scalar quantity called the Lagrangian. This is a scalar quantity. This is nothing but the difference between kinetic energy of the entire robotic system and the potential energy of the robotic system. So the kinetic energy is imparted by all the rigid bodies, all the center of masses of the rigid bodies, and the potential energy is also contributed by all the rigid bodies within the robotic system. So if we have two rigid bodies, KE would be the summation of all the individual kinetic energies contributed by the two rigid bodies. And PE for a system of two rigid bodies is nothing but the sum of potential energy contributed by each of the bodies within the robotic system, right? And based on this, the equations of motion can be obtained with the following relations as. So if you want to obtain the torque that is acting on the robotic system, or tau, if we take the derivative, the partial derivative of the Lagrangian with respect to the joint coordinates, the derivative of the joint coordinates, right? And again, further take the derivative with respect to time, right? Subtracted by the partial derivative of the Lagrangian with respect to the joint coordinates, we will get the vector torque, the torque vector. And this is equivalent to, like, once you have obtained the torque, you can basically assemble this mass matrix, M of Q times Q double dot plus N of Q, Q dot. So all the terms that contains this Q dot, you can basically take out, you can assemble this mass matrix, and the remaining terms, basically you can basically assemble it as a vector named N. Right. So you should also note that this L is a scalar quantity, and this vector Q, sorry, the parameter or this variable Q is a vector, right? So if a robotic system has two rigid bodies like an RR manipulator, this Q would be comprising of Q1 and Q2, like the individual joint variables. So if we have to do this equation twice. We have to solve, or we have to formulate this equation twice with respect to each of these variables, Q1 and Q2. So the first equation corresponding to tau1 would be basically the Lagrange equation with respect to the joint variable Q1. This would give you the tau1. And if you again apply this Lagrange equation for the joint variable 2, you would get the corresponding expression for tau2. Right? And similarly, for if there are n such links or n such joints, you have to take the partial derivatives with respect to n such joints in order for you to get the vector tau. Right? So that is what the Euler-Lagrange method is about. And again, we have to find the general expression for this kinetic energy and potential energy is nothing but this half mv square term that we know so well. So this term VCI is nothing but the velocity of the center of mass of a link. So again, taking from the context of a 2R robotic manipulator, right? So if this is the global frame of reference, X and Y, and each of the links will have a center of gravity or a center of mass somewhere along its link length, and this would be the velocity of the center of mass, VC1, with respect to the global frame. So if I'm taking the global frame as 0, the velocity of the center of mass of the first rigid body would be this term, 0 VC1, and the velocity of the second link, center of mass of the second link, would be 0 VC2. Right? And since there are two such bodies, we have to basically take the summation of all the the individual kinetic energies of all such links. That is where the summation comes across. And we also have one more term that is nothing but the uh, rotational kinetic energy, that is omega transpose ICI omega, where this ICI is the inertia tensor of a rigid body with respect to a frame that is attached at the center of gravity or at the center of mass. Because like the inertia tensor could basically vary depending on where you are, with respect to what frame you are basically referring this inertia tensor. But here, since the subscript is Ci, it says we are referring with respect to a frame that is attached at the center of mass. So the inertia tensor is defined with respect to a frame that is attached at the center of mass. That is what this term basically says, that ICI. And similarly, the potential energy is nothing but the elevation. It's a term that is similar to this mgh term that we know so well, right? Where m is the mass of the individual rigid body, gi is basically the acceleration due to gravity with respect to the ground frame, and 0 pci is nothing but the coordinate of the center of mass with respect to the 0th frame. So like for in the case of a 2R robot, the 0 pc1 term is nothing but the distance from the 0th frame to the center of mass. And for the second body, it will be 0 pc2, that is nothing but the distance from the origin all the way to the center of mass. Right? So that is about the potential energy. And if you apply the Euler-Lagrange formulation, once you determine the total kinetic energy and potential energy, you can actually find out this scalar called Lagrangian. And once you apply the Lagrangian onto this Euler-Lagrange equations of motion, you will be able to obtain the vector tau. So that is about Euler-Lagrange method. You can try a few examples on your own. Like the classical example has been, a classical example of a 2R manipulator has been solved on the live sessions, right? And another method is called this Newton-Euler method. So if you have gone through all the lectures, it should be apparent that it's much more mathematically involved than Euler-Lagrange method. But as the number of rigid body increases, right? If the number of rigid body increases to more than 3 or beyond, implementing an Euler-Lagrange method is not going to be very easy, because finding out each of these terms, 0 VCI, this ICI, are all going to be more and more complicated. And you'll also have to take the partial derivatives with respect to the velocity vectors as well as the position vectors. So it could get more of a headache as the number of degrees of freedom involves. So this is where we have the Newton's Euler equations of motion, right? So as the number of rigid body increases, using Newton-Euler method to derive the equations of motion of a robotic manipulator becomes even more convenient, because we are employing a recursive version or a recursive scheme using this Newton-Euler method. Like, because if we are finding the velocity of the current link, we can use some propagation equations to find the velocities of subsequent links, right? Using this forward propagation. And if we know that forces acting on the end effector, we can actually successively find out all the forces acting on all the joints, coming back from the end effector all the way to the ground frame using this backward recursion. Because you have already seen how to do this forward velocity propagation and backward force propagation as we covered statics, right? But in case of dynamics, a few more terms will also come, because earlier in statics, the robot was assumed to be static, obviously, because, and due to that fact, the terms contributed by the inertia of the robot, right, does not come into picture. But in case of dynamics, the forces are also influenced by the inertia of the robotic system. So a few more terms will also join while deriving the dynamic model of the robot. So it basically comprises of two equations. One is from the conservation of linear momentum, that is the Newton's equation. That is nothing but for a rigid body, the force acting on the rigid body is simply mass times the acceleration at the center of mass of the rigid body. And from the conservation of angular momentum, the Euler's equation is analogous to the linear equation, but it consists of I alpha, the moment of inertia of the robot, times the angular acceleration, plus an additional term called omega cross I omega. Right? The derivation of this Euler equation, you probably won't be able to find out in robotic textbooks. A more convincing derivation, if you want to find out more convincing derivation, you will have to refer some rigid body dynamics textbooks. Right? So yeah, this is the essence of Newton-Euler equations of motion, right? And how to formulate our recursive relations so that we'll be able to finally reach or finally assemble the equations of motion. So our target is to assemble the equations of motion. Tau vector would be m of q times q double dot plus some vector n of q dot. So this is basically our aim. And how we would be able to achieve, or how are we going to assemble these equations of motion from this Newton-Euler equations of motion is what we are going to see in the subsequent slides. So it basically deals with, it essentially deals with the two propagations in two directions. So we'll have to propagate velocities and accelerations in forward direction, and we'll have to trace back the forces and moments acting on the end effector all the way back to the ground frame using something called backward propagation, right? So for example, like if we have an N-link manipulator, so if this is the ground frame, we have a link 1, link 2, link 3, all the way to this end effector. So the forward propagation, like if we are given an initial condition, like if the velocity of the ground frame as well as velocities of each of the individual joints, right? Maybe this is, we can label this as joint 1, joint 2, joint 3, etc., joint end effector. So if we are given the initial condition of the velocity of the ground frame, like it's mostly going to be 0 in case of a fixed manipulator, and we are also given the velocities of each of the joints, maybe if all the links are revolute pairs, you could get angular velocities of all these revolute joints. Then what would be the positions and velocities of the velocities and accelerations of the end effector, right? So omega end effector, then this is angular velocity of the end effector, linear velocity of the end effector, angular acceleration of the end effector, and the linear acceleration of the end effector. How are we going to find this out? How do we find this out? So that is done through something what we call the forward propagation. Forward propagation. Right? Remember that the inputs to the forward propagation model is the initial velocity of the 0th frame. In most cases, it is going to be 0. And we would also want the velocities, the input velocities that we would be giving onto each of these joints. Those are also inputs. our objective is to propagate these velocities all the way from the 0th frame to the end effector frame using some recursive relations, using some iterative schemes, so that will be able to find out these parameters: omega end effector, velocity of the end effector, the angular and linear accelerations of the end effector. Okay, so for that, we have the following propagation equations, as you can see. So if you want to propagate linear velocities, so omega I plus 1 with respect to I plus 1 is nothing but the angular velocity of the previous link. So I'm telling the angular velocity of the next link or the subsequent link is the angular velocity of the current link plus whatever the joint is doing, whatever each of the joints is rotating, right? And don't mind these rotation matrices. These are very important, but the basic fundamental equation is nothing but omega of I plus 1th link is omega of ith link plus whatever that joint is basically doing. If it is a revolute joint, the term would be 0, 0, theta I plus 1 dot transpose. Because this is expressed like if we have two joints, right? If this is ith joint, this is I plus 1th joint. The rotation of this I plus 1th joint will be given by this term theta I plus 1 dot. Right? And this is always going to be expressed with respect to the z axis of the zi plus 1 frame. Right? If you can recall the DH convention, our zith frame is basically the frame zi aligns with the axis of the revolute joints or axis of any joint. So if this is the ith joint, if this is the ith link, in fact, zi would be aligned parallel to the revolute joint over here, and zi plus 1 is going to be aligned with respect to the revolute joint at I plus 1 frame, zi plus 1. So since the revolute joint is already aligned with the z axis, the first two components are always going to be 0. And the third component is whatever the angular velocity the I plus 1 joint has. So that is this term, right? So the angular velocity of I plus 1th link. So this is the I plus 1th link. This is the ith link. So the angular velocity of the I plus 1th link is angular velocity of the ith link plus the rotational velocity the joint, this joint, I plus 1th joint is contributing. So that is what this expression is all about. And in order for us to make it recursive, we would like to specify the angular velocity of the I plus 1 joint with respect to I plus 1th frame. And we would also like to specify the angular velocity of ith joint with respect to ith frame, right? In order for us to make it recursive. So that like if we know 0 omega 0, right? If this is the angular velocity of the base frame, through recursive relation, we should be able to find 1 omega 1, 2 omega 2, all the way to the angular velocity of the end effector frame, E omega. Right. So we basically know I omega I is going to be expressed with respect to the ith frame. We also know that the I omega I plus 1 is going to be expressed with respect to I plus 1 frame. In order for us to make this homogeneous with respect to a single frame, like this does not make sense. All the parameters or all the quantities will have to be established with respect to a single frame of reference. So in order for that, since this is specified in ith frame, we'll have to transform or we'll have to transpose this to I plus 1th frame. So for that, we are using this rotation matrix, transforming from ith frame to I plus 1th frame. That is what this rotation matrix does. And this term is already expressed with respect to I plus 1 frame. Because theta I plus 1 is the angular velocity of the link I plus 1. And that is already expressed with respect to Zi+1 frame. So that is by default with respect to I+1 frame. We don't need to write a special superscript over here because this is already implied. Eta I+1 is always expressed with respect to Zi+1 frame. It should be apparent from the DH convention also. So that is what this equation is doing. And again, like further taking the partial derivatives of this equation, we'll be able to get this equation, that is the equation concerning angular acceleration. And we also have an equation corresponding to the linear acceleration of the I+1 frame. So these are recursive relations. So if we know the angular velocity of the preceding link and the active joint variable, the derivative of the active joint variable of the current joint, we'll be able to find out the angular velocity of the I+1 joint using propagation equations. And similarly, if we know the angular acceleration of the current link and whatever the angular acceleration of the subsequent joint is executing, using these recursive relations, we'll be able to find out the angular acceleration of the subsequent links. So this is how it propagates further and further. And similarly, if we know the linear acceleration of the current link, using the propagation, we'll be able to find out the linear acceleration of the subsequent link. And again, like how to derive these equations, it basically comes from the fact that like this entire equation is derived with we have basically come across this in the previous weeks. So if we have a frame over here, a frame fixed in space, and we have a rotating frame B over here. If we have a frame B, a rotating frame with respect to A over here, and we have a vector Q, right? So this the vector Q is defined with respect to B. So the vector Q, the position of vector Q is defined with respect to B, right? So one second. If we know this, and if we also know the position of the frame B with respect to A, position of frame B with respect to A is also known, then what is the position of Q with respect to A? This is the question, right? This position of Q with respect to A, right? So using law of vector addition, like position of Q with respect to A is position of B with respect to A plus position of Q with respect to B, using law of vector addition. But since we are expressing this entire term, all the terms with respect to the frame A, right? We would like to convert this into frame A because the frame B is rotating with respect to frame A. So that is where the rotation matrix comes into picture. So making that substitution, the rotation matrix ARB times Q P, sorry, BPQ. This is how it would look like. The position of Q with respect to A. That is how it looks like. And how these expressions are derived, how these expressions omega, alpha, or for the rotary case as well as the velocity and acceleration for the linear case, these are all derived from this general expression, by taking subsequent derivatives. So what happens if we take the derivative of this expression? It would be position becomes velocity of q with respect to a. This would be equal to velocity of b with respect to a, plus we'll have to apply the chain rule, arb b bq plus arb dot b pq. This is nothing but the chain rule applied. The first term multiplied by the derivative of the second term plus the derivative of the second term multiplied by the derivative of the first term multiplied by the second. That is what these two equations are about, right? And in the previous lectures, we also know that derivative of a rotation matrix R dot is some skew symmetric matrix omega multiplied by this very same R matrix, right? So this ARB dot BPQ, this term would in turn convert it into a form similar to this. That would be something similar to omega B with respect to A cross R AB, then the term B PQ. So this is the derivative of a vector. Derivative of a vector that is reference with respect to a rotating frame. And we are expressing this derivative of this vector Q with respect to the fixed frame A. And again, if we are further taking the derivative of this equation, we will get the expression for acceleration also. So further taking, this would become acceleration. This would also become an acceleration. You have to apply the chain rule for this equation. So if you are applying the chain rule, you will get two more equations, two more terms from this term. And if you are applying the chain rule to this term, you will get three more terms from this equation. So in total, you will get 5 plus terms actually. For 3 from here, 2 from here, then 1 from here. So 6 terms would come in case of an acceleration expression. And by replacing these indices judiciously instead of A, Q, and B, by replacing it with respect to I plus 1 and ith frame, you will be able to obtain these expressions, right? Instead of position, if you substitute this, instead of this position, if you substitute the expression for angular velocity omega, and further taking the derivative and applying this expression, you will be able to get a similar expression comparable with this equation. And again, further taking the derivative of this term for the linear case, if you are applying the position, this term would correspond to the velocity. And again, further taking the derivative of this expression, you will be able to get an expression comparable with the acceleration, linear acceleration. So that's how it goes. But since this is outer scope of this course, we are not proving, or we are not providing this full proof of the derivation. Right? As of now, you only need to know or only need to understand the forward propagation equations for angular velocities, angular acceleration, and linear acceleration. In the previous section for differential kinematics, we have also given the forward propagation equations for velocities as well. Velocity of I plus 1 with respect to I plus 1 as a function of velocity of I with respect to 1, plus some other terms. This was given in the previous lectures, right? So that is about the forward propagation of velocities and accelerations. And we also have a second stage called the back, again, the forward propagation for, for these expressions are exclusively applicable to rotary joints. Rotary joints, because each of the rotary joints will have a term corresponding to theta I plus 1 dot. So these are terms contributed by the rotary joints. Theta I plus 1 dot theta I plus 1 dot, theta I plus 1 double dot, the acceleration of the revolute joint at that particular joint. So these are exclusively for rotary joint. But in case of prismatic joints, prismatic joint does not have this term, right? It does not have theta. It has a linear moment. It does not have an angular moment. So in case of a prismatic joint, this term vanishes, right? And in this expression, this term also vanishes. This term vanishes. But it can have a different, another few more terms, because it has something called a linear velocity, di plus 1 dot and di plus 1 double dot, right? So this is with respect to prismatic joint, and whatever we have shown in this slide is with respect to rotary joint, right? And this is how it would look like for prismatic joints, right? So angular velocity of I plus 1th link is same as angular velocity of the ith link, but brought forward using this transformation. Because earlier we have seen this term basically vanishes. And the linear velocity of the prismatic joint will be the linear velocity of the previous joint, I omega I, plus this term, omega cross P, the radial term, as well as the slip, the linear term, 0, 0, di plus 1 dot. Right? And these are all expressed with respect to the ith frame. We have to bring it back to the I plus 1 frame. That is why we have this rotation matrix. Right? So because everything is expressed with respect to the current frame I plus 1. So it's simple math, because if we have a frame of reference, if we have a rotating rigid body with respect to the z axis, the velocity of this tip, if this is the ith tip and this is the I plus 1 tip, so Vi plus 1 is nothing but Vi plus omega cross this link length. Let this be P, omega cross P, right? That is exactly this term. But these are all expressed with respect to ith frame. And we are using this rotation matrix to bring it to the I plus 1 frame, just to make it recursive. That is how this equation comes. And due to the fact that this term, the I plus 1 frame will also have its own linear velocity, because I plus 1 joint is going to be a prismatic joint. There is also going to be a linear velocity component. That is why we have this extra 0, 0, di plus 1 dot component over here. And analogous to the angular velocity, the same thing also happens for angular acceleration, because angular acceleration of the I plus 1 joint is same as that of ith joint, but brought forward using this transformation matrix. There are no other terms because this is a prismatic joint. But in the case of the linear acceleration, we have how many terms? We have a term over here, one term, term 1, term 2. This is the tangential acceleration, alpha cross r. This is radial acceleration, omega cross r. This is something called a slip acceleration, di plus 1 double dot, and this is what we call the Coriolis component, 2 omega cross this term, d. Right? And you can basically obtain this same structure just by the case that we have considered earlier. Like if you take a vector expressed with respect to a rotating frame, if you take subsequent derivatives, this would be the first derivative of the vector, and again taking derivative of this expression, you would get around 6 equations, somewhat around 6 equations, and that would be comparable with this large expression over here. A general structure would be similar, but by judicially replacing these indices A, Q, B with respect to by making judicial choices, I+1 and ith frame, you will be able to obtain this exact expression, right? And you could also use any textbook regarding rigid body dynamics. They'll have precise or clear definitions with respect to how to differentiate a vector with respect, defined with respect to a rotating frame of reference. And yeah, so far we are still in a forward velocity propagation. We have seen the cases of a revolute joint earlier. We have also seen the case of a prismatic joint now. And yes, we have something called backward propagation of forces. So far we have propagated in the forward direction. Okay, so this term is not correct. This is, in this slide, we are dealing with the backward propagation. So earlier we have seen how to propagate forces. Now, if we are given an end-linked manipulator like this, I'll roughly draw. So far. So this is the end effector frame, and we have a 0th frame, right? So if we are given the forces acting on end effector Fe and the torques acting on end effector, using backward propagation, we'll be able to determine the torques acting on each of the joints of the robot. Torque acting on this joint, torque acting on this joint, torque acting on all the joints using what we call the backward propagation, right? So the backward propagation is the results of the externally applied forces, that is forces acting on end effector. It could also be influenced by the forces, the torques or the wrenches acting on the links of the manipulator, external forces, right? And it is also contributed by the inertia as well, rotational as well as translational inertia of the robot. So that is what we see over here. So now we apply the Newton-Euler equations of motion. So this is the Newton's equation, right? The inertial force acting on the ith link is nothing but mass of the ith link multiplied by the acceleration of the center of mass of the ith link, right? So if we have a link like this, right, and this is a link, and we have an ith frame over here, and we have a subsequent link over here. This is link I+1, this is link I. We have a frame I+1 over here, right? And we have the center of mass over here. This is center of mass, right? And it says the inertial forces that is acting on the center of mass, that is expressed with respect to the ith frame. So this is ith link, and the frame that is attached to the ith link is ith frame, right? So the inertial forces is nothing but mass times acceleration. Acceleration of the center of mass expressed with respect to the ith frame. That is why we have this superscript. And the subscript denotes the acceleration of the center of mass, and it is expressed with respect to the ith frame. That is what the superscript denotes. But we haven't basically given out how to obtain or how to determine this term, acceleration of center of mass. Again, like if you go back to the previous equations, like if you go back to this previous equations, this lengthy expression, like if you substitute some of the key terms onto that could be applied to this situation, you will be able to get this expression, because the acceleration of center of mass is nothing but the acceleration of I acceleration of this point, ith frame, plus the tangential component, that is alpha cross, if ith frame has an angular acceleration I alpha I, and this quantity IPCI is nothing but the distance between the frame I and the center of mass. Right? This is nothing but this distance. So alpha cross P would be the tangential component, and omega I cross this distance would be the centrifugal component. Right? That is nothing but this equation. Right? And now we come on to the Euler equation. We have seen this earlier. Euler equation would be ICI, that is the inertial tensor expressed with respect to a frame that is attached here at the center of mass times I alpha I. Right? So I alpha I would be, we have already obtained this expression for I alpha I using forward propagation, plus I omega I cross ICI times I omega I. So we all know these, all these terms. We know this from forward propagation. We also know these terms from forward propagation. And based on the geometry of the rigid body, we will also be able to find out this term, ICI. Right? And if you know these terms, if you know the inertial terms, IFI and INI, you can use the backward propagation. You can basically use the backward propagation to find out the joint torques and the joint forces and the joint moments of all of the joints. So we begin backward propagation basically begin from the I+1 frame, right? I+1 frame, and since this is expressed with respect to I+1 frame, we have to bring it back to the ith frame using this rotation matrix, and we also have this inertial component IFI. So if you take the free body diagram of a rigid body, ith rigid body I. So this is the ith frame. This is rigid body I. This is I+1 frame. So at the center of mass, we have the inertial forces. We have the inertial moments. And at this end, we have the reaction forces contributed by I+1 frame, Fi+1 with respect to Fi+1. And we also have the moments Ni+1 with respect to I+1. So the forces would be, if you do a force balance, the force acting on this side, on ith frame, IFI, we also, I small fi, and we also have I small ni. Because the capital F and capital N denotes the inertial terms, and small f and small n denotes the forces and torques acting on the joints. So if you do a force balance, just by considering the forces alone, IFI would be sum of this inertial forces Fi and the forces acting on the I+1 frame. That is nothing but this expression. And if we do a moment balance, INI would be the moment contributed by the inertia, right? This term, that is this term. We also have a moment contributed by the I+1 frame, that is this term. We have it over here. So I'll just mark it permanently. We have covered this term, we have covered this term. And we also have a moment contributed by the inertial forces. There will be a distance P, if this is the distance between ith frame to the center of gravity. So P cross Fi would be the moment contributed by the inertial forces, that is this term, right? And the moment contributed by the forces on the I+1 frame. So that is this distance. that is denoted by I P I plus 1. This distance cross this force, that is this term. But but if we are applying the correct reference frame, we have to pre-multiply it with the correct transformation of the rotation matrix. Wherever it is applicable, it will come. It will have to come. So that is the backward propagation. So we'll be able to obtain the forces acting on the joints and the torques acting on the joints. And these are all 3x3 vectors. Like the small f would be fx, Fi, Fz, and the torque vector would be Nx, Ny, Nz. And since these are all expressed with respect to the current frame, if we are interested to find the joint forces acting at that particular joint, we only need to extract Fz or Nz. Because we all know by DH convention, the Z axis always aligns with the joint axis. So if the joint is a rotary joint, we'll only have to extract the NZ term to find out the joint torque. If the joint is a prismatic joint, we only have to extract the force term, Fz. Yeah, that's about it, the propagation. So depending on the kind of joints, we can basically, this could become tau or this could become tau, depending on the joints. Right? And using backward propagation, we'll be able to successively find out all the joint forces or the joint torques whenever it is applicable. Yeah, and with that, we'll solve some sample questions regarding week 5 using whatever we have discussed. So yeah, question 1, it says, in a serial or a fixed base manipulators, the velocity vectors of individual joints can be obtained by backward propagation. Is it correct or is it false? Saurav, are you still there? Can you answer this question? Okay. I suppose not. Yeah. Okay, so we have basically established how to propagate velocities, that is using forward propagation. So velocities and accelerations are propagated using forward propagation. And the forces and torques are propagated from the end effector all the way back to the ground frame using backward propagation. And here the question basically says, in the case of serial manipulators, velocity vectors of individual joints can be obtained by backward propagation. We know for a fact that that is false because velocities are propagated using forward propagation. Right? So the correct answer is going to be false in this question, for this question. Okay, so moving on to question 2. Again, these are expressions for accelerations. It could be a bit tricky to know or identify which of these equations is correct. But if you apply a bit of a logic regarding whatever we have discussed in the session, it could be fairly straightforward. So it says the linear acceleration of model of a rotary joint. Like if the I+1 joint is a rotary joint, how would the accelerations be propagated from ith joint to the I+1 joint? So we need to find acceleration of I+1 joint. We have ith joint. This is how we propagate. Then we'll also have at a the tangential term, tangential acceleration component, that would be alpha I cross the link length I+1. And we also have a centrifugal term I omega I cross I omega I cross IP I plus 1. And if you are familiar with the DS notation, these are all expressed with respect to the ith frame. This is expressed with respect to ith frame. And these entire terms are all expressed with respect to the ith frame. But for us to make it recursive, we would prefer AI plus 1 to be represented with respect to AI plus 1 frame. So for that, we have to multiply all the terms that is in the ith frame with respect with the appropriate rotation matrix. That is, we have to transpose it from ith frame. We have to transpose it from ith frame to the I plus 1 frame. Right? So in that regard, which would be the correct answer? This is the forward propagation equation. So in that regard, I guess the correct, this has a minus over here. Yes, this is not correct. Equation 2 appears to be correct. Yes, this appears to be correct. Equation 3 and 4, if you can see, the rotation matrices are basically inverted. Right? So these are not the correct rotation matrices. We want to bring the rotation matrix from I to I plus 1 frame, not I plus 1 to I frame. So in that regard, these two are false. Here we have a minus sign over here, and this expression also is inverted. So the correct option is option B. Okay, yeah. Thanks for responding, Saurav. Okay, moving on to question 3. This is a numerical problem. What does the question say? It says, in a single rotary link manipulator, planar link manipulator, the motor is connected with the rotary joint rotating at a uniform speed of 2 radians per second. And the distance between the base frame to the end effector point is 0.5 meters. What will be the radial or centripetal acceleration component of the end effector? So it's a straightforward question. You have been given the angular velocity as 2 radians per second. 2 radians per second. We also have the distance between the base frame all the way to the end effector as 0.5 meters per second. And we are asked to find out the radial acceleration component. So what would be the answer? The radial component of acceleration. What would be the answer? So like we know it's the radial component or the centripetal component would be omega cross r, right? So what is omega? So we basically know that omega is always expressed with respect to the z-axis. So omega would be 2k, right? 2k cross, and the link length. With respect to what frame does, with respect to which axis do we specify the link length? This is always going to be specified with respect to the x-axis, right? If you can recall the DS parameters, we use this term AI plus 1, right? That is the translation along x-axis to map or to get the link length into the model, to acquire the link lengths into the model. So the link length is basically along the x-axis, and the rotations are about rotations and translations. The velocities are always going to be with respect to the z-axis. So if you do this 2k cross 0.5i, what would be the answer? So if you take these two terms, it'll be 2 multiplied by 2.5. This would be k cross i would be, what is k cross i? That is minus j, right? This would be minus 1j. And we have this term over here. So remaining would be 2k cross minus 1j. So it would be k cross j would be minus I. We have, sorry. I think I made a mistake. K cross I is j, right? This term. K cross I is j. This would be 1j. And we also have a 2k term remaining, 2k cross 1j. K cross j is minus I. So this would be minus 2i. So in that answer, the correct option is 2. It's not minus, it's minus 2, it's not 2. Okay, moving on to question 4. It says the specification of the robot position as a function of time is called trajectory. Is it true or false? So if you know the position alone, like if you travel, it does not matter. Without considering the time, you can basically arrive at each of these points at any time you want. But that is different if you are given some time constraints. How you would be traversing through this given path will always going to be a function of time, right? Without the consideration of time, this is nothing but simply a path. But if you are given a time constraint, this would become functions of time. So what would this become? This is nothing. This is called a trajectory followed by the position q. So in that regard, the option is indeed, the answer is indeed true, right? Specification of robot position as a function of time is called trajectory. So without the time in picture, it would be simply called a path. But now, since we have the time in picture, it's called a trajectory. So in that regard, the answer is indeed true. Okay. If you are there, you can respond. If you know the answer, you can actually let me know. You can unmute yourself or you can use the chat box. Okay, so moving on to question 5, it says, for a given manipulator, the ith joint angular velocity is so and so, and the acceleration vector is again so and so. If the position vector I plus 1, position vector of I plus 1 joint with respect to ith joint is given as so and so, then the tangential acceleration of I plus 1 joint with respect to ith joint is. It's a tricky question. We'll write these quantities one by one. So question 5 says omega I, angular velocity omega I is 0, 1, 2, and acceleration vector alpha I is 0 to 1. Okay, if the position vector of I plus 1th joint to ith joint is given as so and so. So by the notation, or whatever we are following in the course, it will be position vector of I plus 1th frame with respect to the ith frame is given as 201. Then the question is asking the tangential acceleration of the I plus 1th joint with respect to ith joint. So tangential acceleration is nothing but I alpha I cross IP I plus 1. This is the tangential component. So if you take the cross product, it would be something like 0I plus 2J plus 1K cross product 2I plus 0J plus 1K. Right? So what would be the final answer? If you take the cross product, it would be, let me check. This term cannot multiply with any of these terms. So taking the second term, 2j cross 2i would be minus 2, sorry, it'll be minus 4k, and 2j cross 1k would be plus 1i, plus k cross I would be 2j, k cross j is 0, k cross k is also 0. So this would be the final cross product. This is I plus 2j minus 4k. Is that correct? But I don't think we have an answer that 1, 2, minus 4. Let me cross check this once again. This component does not have any value. So 2j cross 2i would be minus 4k. And this would be 0. And 2j cross 1k would be 2i. Yes, this would be 2i. Yes. So the answer is 2, 2 minus 4. Do we have that option? 2, 2. Yes, we have this option. 2, 2 minus 4. I hope this is clear. Let me know if this is not clear. Checking the option, the correct answer is indeed 2, 2 minus 4. Okay, so moving on. This is again a sub-question of the previous question. We already have all the terms. Now it's asking us the centripetal acceleration instead of radial acceleration, instead of tangential. So again, we have the same terms. We have the angular velocity, omega I would be 0, 1, 2. And the position vector of I plus 1 frame with respect to the ith frame is 2, 0, 1. And the centripetal, the radial acceleration or the centripetal acceleration, as you know, would be omega cross, right? So how would you do that? It will be 0, I plus 1j plus 2k cross 0i plus 2j plus, 0i plus 1j plus 2k cross 2i plus 0j plus 1k. So first we'll solve the term that is contained within the square brackets. So what would that be? So 0 does not have any components. This will all be 0. So 1j cross 2i would be minus 2k. Then 1j cross 0j would be 0. 1j cross 1k would be, j cross k would be 1i. Right? Then we have 2k cross 2i would be 4j. Then 2k cross 0j would be 0. 2k cross 1k would be again 0. K cross k is basically 0. Minus 2, 1, 4. Again, we'll have to cross it with 0i plus 1j plus 2k. So again, the 0 terms will have no components. These will all be 0. We'll begin with this term. So 1j cross minus 2k. That would be j cross k is I. We have a minus sign over here. So it will be minus 2i. Then 1j cross 1i would be minus 1k. Then what do we have? 1j cross 4j, that would be 0. J cross j would be 0. Then plus 2k cross 2k would be 0. 2k cross 1i would be 2j. 2k cross 4j would be minus 8i. So this would be minus 10i plus 2j minus 1k. So this would be minus 10 to minus 1. That would be the correct answer. Right? It's just it's all about taking cross products. That's all this question is about. You need to identify what are this expression corresponding to the radial acceleration, and as we have seen in the previous question, the tangential acceleration. Yeah, so that is about it, the answer. We have up to 12 questions, so we have reached question 7. So this is a fairly straightforward question. It says, for a given single rotary link manipulator, as seen in the figure, what will be the potential energy? What would be the if you are still there, can you answer? Can you guess this answer? The potential energy to be? This is the y component. If this is the x component, potential energy would be the elevation of this ball with respect to the common datum. If we consider this to be the datum, potential energy would be the height. This would be the height. So it will be mg times the height. So we know that this term, this h, what will be this h? So if this is theta, mgl cos theta. Yes, it will be mgl cos theta. Because this is theta, this is L, and this would be L cos theta. That is the height. Potential energy would be GL cos theta. So no scope of confusion in that. That is indeed the correct answer. Yes, GL cos theta. Yeah, same question, but what would be the kinetic energy? So we also know that kinetic energy is nothing but half mv square for a point mass, and v is nothing but x velocity, x dot square plus y dot square. V square would be x dot square plus y dot square. What is x? Based on this expression, x is minus L sine theta, y is L cos theta, right? What is x dot? That would be minus L cos theta, theta dot. Y dot would be minus L sine theta, theta dot. So x dot square plus y dot square would be L square cos square theta dot square plus L square sine square theta dot square. So this is nothing but L square theta dot square, because cos square theta and sine square theta is 1. So this is your V square, right? So the remaining term is m by 2. So that would be m by 2. So this would be the answer. And theta is nothing but omega. So they have given a new term instead of theta dot, they have chosen to give it as omega. So in that regard, the correct answer would be ml square omega square. I guess this is the answer, right? No, sorry. That is ml omega square, I guess. This is the correct answer. Option C. Yeah, option 3. Thank you. That is indeed the correct answer. Question 9. Yes, again, this is a question regarding backward propagation. If you're still there, could you identify which of the option would be the correct answer? If you consider a rigid body I, at the distal end, sorry, at the proximal end, you have frame I. At the distal end, you have frame I plus 1. We also have the center of mass. This is center of mass. And the forces at this point, at ith frame, would be small f, I with respect to I. The moments would be I and I. And at the distal end, the forces would be I plus 1 f I plus 1. The moments would be I plus 1 n I plus 1. Then we have the inertial forces. Fi with respect to I, and the inertial moments Ni with respect to I. So for the backward propagation, we need to find out the moments I and I from in plus 1. Sorry, I plus 1 and I plus 1. We need to propagate the forces backward from I plus 1 to I5. So we have I plus 1 and I plus 1. Then what else do we have? We have the force here, the moment contributed by the force, right? That would be this distance cross this force. So this distance would be, as per our convention, that would be Ti plus 1 with respect to I. So we have Ti plus 1 with respect to I. And since this force is with respect to I plus 1 frame, we have to bring it back to ith frame because everything is written in terms of ith frame. So we have I R I plus 1, I plus 1 F, I plus 1, right? So we have taken this term into consideration. We have taken this term into consideration. Then we have these two terms, I and I, that is already expressed with respect to the ith frame, I and I. Then the force, the moment contributed by the inertial forces, right? That is this distance. We have this distance actually, that is as per our convention, that is IPCI, the distance of the center of mass with respect to the ith frame cross IFI. So we have taken that into consideration. What else is remaining? Nothing else is remaining, right? We have taken all the moments that is contributing to the moment I and I. So in that regard, which is the correct option? We have, this term, we have to bring it back to the ith frame. So the correct rotational matrix would be I, R, I plus 1, right? So in that regard, option 2 is, I guess, is your final option. Let me check that, option 2. So this term matches, this term matches with our own term. And we have this INI term that is also matching with our term. This term is also there. Then, this term, final term. Yes. So in that regard, I agree with you. The answer is indeed option 2. Right? Like as you practice or as you put a more thought into this, it'll be more clear, like what would be the correct expression for forward propagation as well as the correct expression for backward propagation. Yeah, so in that regard, the answer is indeed option 2. Moving on to question 10, it says, in serial or fixed base manipulators, the forces and moment vectors of individual joints are obtained by backward propagation. Forces and moments by, forward propagation. That is what the question says. So we have seen a similar question at the beginning of the session. It is forces and moments are always obtained through backward propagation. It's not forward, it's backward. So in that regard, the answer is false. So moving on to the second last question, it basically says, if M of mu is the inertia matrix in task space and J of Q is the Jacobian matrix, what will be the vector of Coriolis and centrifugal effects in task space? So this is a fairly involved question. I guess we have come across the transformation of the dynamics equation of motion in task space and joint space. Because in joint space, this is how you write the equations of motion. M of Q, Q double dot plus N of Q, Q dot. This is in joint space, right? Because this tau is nothing but the torque acting on each of these individual joints. And these Qs are the joint vectors, the joint variables. Position, velocities, accelerations of the joint coordinates. Whereas if you could also write this equation in, yeah, I guess you have given your answer as option 4. But how did you arrive at that option? Can you justify that? In task space, this equation would be M of mu, mu double dot plus N of mu, mu dot. This is task space. Whether that option is correct or not, I cannot say for now, but I'll have to derive that. Because we'll derive from the known equation, well-known equation. Tau is M of Q, Q double dot plus N of Q, Q dot. This is equation 1. And in the previous session, we have actually, from the principle of conservation of power, principle of conservation, from conservation of power, we know the relation between the joint space branch vector and the task space branch vector that was found to be tau would be J transpose F. We have derived this in the previous session, that is equation 2. Right? So substituting 2 in 1, we will get J transpose F is M. I'm not writing the brackets. I'm assuming that to be function of Q, Q double dot plus N. Let this be equation 3. And what is the kinematic mapping between task space and joint space? So from kinematics, we know the task space velocities. Mu dot is J, the Jacobian vector, times Q dot. Right? So if you differentiate it further, mu double dot would be J of Q double dot plus J dot Q dot. This is equation 4. Applying the chain rule, that's how we get more terms. So again, substituting 4 in, sorry, I'll move here. So 4 in 3, we will get J transpose F is M of, instead of Q double dot, I am substituting this entire expression. So that would be J of Q double dot, right, plus, is it correct though? Okay, J dot sorry. It's a slight mistake. So instead of this Q double dot, from this expression, what is Q double dot? So again, I'll have to further manipulate. So Q double dot would be mu double dot minus J dot Q dot, the whole pre-multiplied by J inverse. This is equation 4. So instead of the Q double dot here, I'm substituting the expression for Q double dot from equation 4. Right? So now equation 3 becomes J transpose F B M multiplied by J inverse mu double dot minus j dot q dot. Then we also have this n term. So simply by expanding, J transpose F would be M J inverse mu double dot minus J dot Q dot. Sorry, now it would be M J inverse J dot Q dot plus M. Now I'm bringing this J transpose to this side to from LHS to RHS. Now what will we get? We'll get F equals J inverse transpose. Should be careful. M J inverse mu double dot minus J inverse transpose M J inverse J dot Q dot plus J inverse transpose N. And we basically know the coefficient of this term. Acceleration term is always going to be the mass matrix, right? So this is always going to be the mass matrix. So I'm highlighting this. J inverse transpose Mj is the mass matrix. So we also have a similar term over here, right? So I'm substituting J inverse transpose M J inverse as M mu. Sorry. That is the mass matrix in task space. Right? Now I can write F as M mu double dot minus M mu J dot Q dot plus J inverse transpose N. Now this would be your, this entire term would be your new vector of centrifugal and Coriolis component in the joint space. Sorry, in the task space. This term, this would be your N mu. So that is how you derive the expression for this equation. So we'll see whether that is the correct answer. You have said it to be option 4. So we have J inverse transpose N. That is correct. Then we have minus mu J dot Q. Minus mu J dot Q dot. Yes, that is. So that is indeed correct. Option 4 is indeed correct. But this is how you arrive at this expression. That is indeed correct. So yeah, moving on to the final question. So it says, the angular velocity of the ith link expressed in its own frame is I omega I is 201. So we'll write these terms. I omega I is 201. Moving on, it says the angular acceleration vector of the same is 220. So we have also been given as I alpha I as 220. And the next sentence says the following link I plus 1 rotates with an angular velocity and axillary acceleration of 2 radians per second and 3 radians per second square. So theta I plus 1 dot, this would be 2 radians per second. Theta double dot I plus 1, this would be 3 radians per second. Both along the z-axis of their own coordinate frame. And we have also been given the rotation matrix I R I plus 1 to be minus 1, 0, 0, 0, 0, 1, 0, minus 1, 0. So determine the angular acceleration of the new link I plus 1 alpha I plus 1. So we have to know the expression. So if you want to go back to the forward propagation equation, like as we have discussed, is the expression I plus 1 alpha. I plus 1 is, we write the subsequent terms. We have this term over here, I, the previous angular acceleration, plus the tangential component, that would be omega I, sorry, yeah, we, in case of this thing, the correct expression would look something like this. I omega I cross 0, 0, theta I plus 1 dot, then plus 0, 0, theta I plus 1 double dot. And this entire term would be brought back to the I plus 1 frame, sorry. This entire terms would be brought to the I plus 1 frame. This is how the forward expression of the velocity propagation equation would look like. Derivation is not provided, but it can be, if you want, you can actually find out how to derive this expression by, it's all derived from the derivative of a vector that is defined with respect to a rotating frame of reference. Okay, so this is only a matter of substituting all the parameters that have been given in the question into this expression. So what do we have? I alpha I, in this question, we have that to be 2 to 0. Okay, before that, we'll first evaluate the cross product. We'll evaluate this term, the cross product. That would be 2i plus 0j plus 1k cross product with 0, 0, sorry, mixing the convention, that would be 2k. Right? Because theta I plus 1 is always expressed with respect to z-axis. Theta double dot I plus 1 is always going to be expressed with respect to z-axis. So this is nothing but 2k. So evaluating this cross product, what do we get? I cross k would be minus j, that would be minus 4j. 0 multiplied by 2 is 0. K cross k is 0. So this term is nothing but 4k, I suppose. Yeah. So this term is 4k, minus 4k. Right? So bringing back, we can evaluate all the terms within this entire bracket. So I alpha I would be 2 to 0. Then whatever we have got by evaluating the cross product, that would be 0 minus 4, 0. And this end result will have to be multiplied by a rotation matrix, that is minus 1. Yes. That is minus 1, 0, 0, 0, 0, 1, 0, minus 1, 0. This thing added with 0, 0, 3. So now what do we have? Multiplying this thing, we will get 2 minus 2, 0. Right? This multiplied with. Okay, so beware, as per our expression, the correct rotation matrix is I plus 1 Ri. But in the question, we have been given the transpose of it or the inverse of it. I Ri plus 1. So in order for us to evaluate this thing, this is the correct rotation matrix. We'll have to invert the rotation matrix, or you could simply just take the transpose because R is an orthonormal matrix. So taking the transpose, it would be minus 1, 0, 0, 0, 0, 1, 0, minus 1, 0. This thing added with 0, 0, 3. So evaluating this term, the first term, that would be evaluating the matrix multiplication term, that would be minus 2. The second row would be 0. The third row would be minus 2 again. Then added with 0, 0, 3. This would be minus 2, 0, 1. This would be your final answer. So in that regard, the correct option is option E, option 5, minus 2. Sorry. I guess the correct answer is minus 201, option B. All right. Yes, that is indeed the answer. Okay, so that is essentially the end of the session. I know this has been quite a bit of a hectic session, but thank you for staying until the end. It's, I guess, this would be the most difficult part of the course. From now onwards, it should be subsequently more eased out. It shouldn't be as hard as the topics that we have covered so far. It should be a bit more relaxed. But again, like understanding the concepts, you will have to. It's not mandatory that you have to go with some textbooks in rigid body dynamics. If you can derive this equation on your own with some logic, it should be fine. It should get you through deriving the propagation equations, the forward propagation and the backward propagation. And in that regard, I only think the difficult equations are regarding accelerations, only regarding accelerations, because all the other things you can simply, you can actually write it on your own. You can derive on your own within a reasonable amount of time. Only the acceleration equations, the angular acceleration and the linear acceleration terms are a bit tricky. Apart from that, all the other equations are of the force equations, the velocity equations, those are all those equations seem straightforward. So if you are able to reproduce these equations for solving the problems, then you should be fine, right? And the Newton-Euler equations are also fairly easy to apply also. The only tricky thing is the acceleration terms, that's all. So yeah, with that, I am winding up the session. So yeah, if you are still there, you can log out. Otherwise, if you have any questions, please let me know. Yeah. Okay, thank you. Thank you. So I'm assuming you don't have any further questions. Okay, thank you.